Wait, it's asking me to download a new app? This one. That's weird. I'm trying an experiment. We shall see if it works. So far, all my experiments have failed, but it has not yet stopped me.
It says you have to enable remote view for people to see it. So.
Okay, yeah, no, it's, yeah. Please select a receipt. Yep, it failed.
Okay.
Login failed. Try again. I will try one more time. Huh, something happened. Hey, change the IP of me. Maybe that's.
That doesn't seem right. It just changed it back to the other one.
It's very bizarre. I don't know what's going on. I mean, the screen has changed or something has happened. But I don't know what's going on.
It's a 14 second video which is
Sorry?
14 seconds video is approved.
When? Just now?
So what?
Oh shoot, okay. I don't want that. That's bizarre. Huh?
When you work with data, it's just a 14 second.
That's totally bizarre. Okay, I don't want to do this.
Yeah,
Okay, you know what? Screw all that. I'll go back to try it and test it. Try it and test it. All right. Just as a reminder, since assignment deadline is coming, so I do have office hours after class, in case you need it. I think you don't, but I'm happy you do. Okay. Let's see. There we go. All right. So, as you recall, we were talking about subset sums, and we went through this entire procedure to design an algorithm for subset sums, including looking at ways to do it, counterexamples, and then coming up with different methods. We came up with a divide and conquer approach, and we realized that while it works, it's not very efficient, unless S is very small. If S is very small, that might be okay. But then we were thinking, is there a better way to do this? And we came up with a recursive formulation, right? Which is, again, a different recursive formulation that had the nice property of having many fewer subproblems to worry about. Specifically, we only had two subproblems, two dimensions of subproblem, an index saying which suffix of the list of numbers you were going to be examining, and a number saying what target sum you wanted to achieve with that subset. And so once we said we all can write this down, the total number of subproblems is this, and we can solve problems. Okay. So that's where we stopped. And again, like in any problem that involves recursion, you want to prove that it's correct by induction, which basically means that you have to show that this procedure here, and we talked about this, is correct by induction, and we talked about how that would work. And then we have to show that it works, that the running time is efficient. And here is where we differ from divide and conquer. Divide and conquer said, look, you have the recursive procedure, use the master theorem to reason about the recurrence, and you're done. Here you don't want to do that because the recurrence as implemented would be terrible. Since you're going to implement it bottom up, you analyze it differently by looking at exactly how many cells you update in every step. And we observe that there are n times s cells in this grid, and every time you have to add a new cell and fill in a new value, you have to look at 2 previous cells. So the overall running time is going to be a constant times n times s, and that's the running time of the algorithm, right? We didn't mention in great detail how you actually reconstruct the solution, but I think it should be fairly clear from here is that every updated value, if you look at the algorithm, let me scroll back to the algorithm here, right? The algorithm says, the algorithm as written is just doing a Boolean combination of things. But you can think of the algorithm as basically saying, look, if this is true, then I've picked xi to be in my current idea for what the solution should look like, and I'm looking at that problem. If this part is true, then I'm saying don't pick xi and look at how to pick your subset from whatever you picked before and what's left, right? So in some sense, the choice of which of these fires to 1 is telling you, did you pick this element or not, right? And of course, if they're both 1, then the answer is it doesn't matter whether you pick it or not. If you think about that, and you go down to the actual procedure of filling in the table, right? When you actually write your code to fill the table 1 by 1 by wrapping it up, you're basically saying this element looks at 2 previous elements, takes the best value it gets from either of them, right? And then puts that, checks which one allows it to continue, and then moves on, right? And so if it chose to get a 1 because this was 1, it's saying, oh, I picked item 2. If it chose to get a 1 because this was 1, saying I did not pick item 2. So in some sense, if you look at where this value became 1 from, and if you can annotate that in the data structure by saying, okay, did I get it from here or from here? At the end, when you're finished and you're up there and it's a 1, you can say, okay, I got its value from here. Okay, that means I picked 2. I got its value from here. Okay, that means I picked this. And you can trace back all the way to the beginning, seeing which elements you actually ended up picking. So that dynamic program, there's always this first step of filling out the answer to get to the end. And then there's this backward step of reconstructing the solution that got you there, right? There is the, is there a subset? Answer yes. And there is the, what is a subset? By backtracking, okay? And generally speaking, the backtracking doesn't take much more time, but of course we have to make sure it doesn't take a lot more time. It is rare that you would have to do more than go back over every single element of the set. In this case, it's even simpler than that. You're just taking one linear time and 1 for each cell. But even if it took going through all of them, you've already accounted for that time by going forward. So it's only a constant times that. So asymptotically, the backtracking step is not going to usually change things, but you should actually check it. Okay, so the whole design process for dynamic programming has this idea of, again, formulate a recursive problem, but specifically one in which even if subproblems overlap, there aren't too many subproblems overall. Write down the recursion to prove that it is in fact correct by induction. But when you implement, observe that because there are a few subproblems, see if you can unroll the recursion and implement the subproblems backwards from the bottom to the top. And then use this backtracking if needed to recover the actual solution. Okay? And that's how dynamic programming works, which is why I think the name is so terrible. That name has nothing to do with that description. Right? So the smart recursion bottom-up thinking is maybe a better way, but not so concise way of thinking about what this is really doing. Okay, so think recursively, implement bottom-up. Okay. When we talked about, okay, so first of all, let me stop and sort of allow us to sort of digest what I just said. And this is a good time to pause and see if you have any questions also about what I just said or what we said last time. Any other clarifications or questions you might have? Yeah.
When you said backtrack to find solution, we have to prove that's correct, our solution is correct.
Yes, it must, yes, you do have it. And so the way you prove it is essentially the way I reason. You will say the following. My backtracking solution is to, when I'm building up the dynamic program, to keep an annotation in each cell saying where its value of 1 came from which side of the recursive, of which cell it came from. If it came from both, I just pick arbitrary 1. So at the end of the first stage of the algorithm, every cell has an annotation saying where its 1 came from. To do the backtracking, I look at the top cell. If it's 0, that means I couldn't find a solution. If it's 1, that means I did. And I will now look at where its 1 came from. If it came from here, I will not put anything in my set. If it came from here, I will put something in my set, and then so on. The reason this is correct is because if we look back up at the recursion, the recursive formulation, which we had proved was correct, that is exactly how it is. Right? Okay, good. Other questions? Can you scroll? Yeah. Did the algorithm? Yes, so this is a recursive formulation. And what I was saying was here, if you naively implement the recursive formulation, you can quickly reason that this is not going to work very well. And that's why you don't want to influence the dividing function, right? But you want to observe that in fact there are very few subproblems. Okay. All right. If you think about the 2 examples I've given you so far of dynamic programming, the Fibonacci sort of computation and this one, you can see a certain layering of complexity. Right? In the first case, it was merely a matter of keeping track of your answers. In the case of the Fibonacci sequence, and once you kept track of your answers, you were fine. In the case of this, it was a matter of designing the correct recursion. A bad recursion would not work, but a good recursion would. In Fibonacci, the recursion was given to you by definition. The definition of the Fibonacci number was the recursive formulation, and all you do is keep track. Here, we had to think of the recursive formulation that would get you. The next problem I'm going to talk about, which is called the knapsack problem, adds one more layer of complexity to this. So to think of the knapsack problem, if you haven't heard of it before, you should imagine yourself as a clever art thief in a gallery at night. You've broken in, you've gotten into the rooms, you have all the artworks, you have your knapsack with you. There's a special exhibition on miniatures going on. So they're all small. They fit in your knapsack. And you did it, but now the alarms just went off. And you know you have about 2 minutes, okay, to get what you can and get up before the security arrives. So you have 2 minutes. It takes you a certain amount of time to pick up something and put in things. You know you can only capture a certain number of things. And your knapsack is heavy. And it will be heavy once you have it, at least once you carry it. But you know, you're gonna sell these to a fence. You're gonna try and make a profit off it. How do you choose which ones to pick so that you gain the most profit while realizing that your bag can only carry some?
More cost and less weight.
More price, I guess, and less weight. Yeah, more price and less weight. And you're a very good assessor of price and weight. They're all different sizes. They weigh a little different amounts. But you're a pretty good assessor of what the overall cost is. You're not only being an art teacher, an art connoisseur, so you're an expert at everything. So then you look at those. Okay, I know this cost. I know its weight. Should I put it or not? You got to make a decision. So this is the problem. So in the knapsack, the problem is the following. So you're given a knapsack, which is sort of, imagine the knapsack, of capacity, let's call it C, okay? And you have items, 1 through n. Each item has a size. So item has size Ci and value Vi. C for cost, C for, because I want to use that for capacity, and value Vi. And my goal is find Okay, let me put an extra twist on this. I actually didn't break into the gallery, I broke into the warehouse. Underneath the warehouse where they stored them. So they actually have multiple copies. So if I like one miniature that's great value, I can take more copies of it. Okay. So for each item, there are, let's say it's many copies of it, many more than I could possibly imagine taking. Right? So my goal is to find a collection of items and the amount of each item. Right? Such that, so let's say at each item I pick ni items in that. So I want to make sure, I want to maximize sigma ni vi such that sigma ni ci is less than. Okay, does the question make sense? Of an amount of each item on ni. Right? Okay. So there are different ways you can approach this problem, and in fact, we will be soon turning to another class of techniques for solving problems called greedy algorithms. Which the thing that you might intuitively think of is, I should just pick the item that has the biggest value for money, right? So you think of the ratio of VI divided by CI, and I want to pick the item that has the maximum amount of that. You will see very quickly, well, no, you won't see very quickly, but you will see, if you play with some examples, that this will not work. In the sense of, it will not give you the best answer, the maximum. The difference, so the twist here in this problem is that I don't want a subset or a collection. Like in subset sum, I said, give me a subset that works. Here, I don't just want a subset that works in the sense of being fitting in my bag, because the trivial answer to that is don't take anything. I want something that's of maximum value. So there's a notion of optimization here that wasn't there in the previous problem. And this is important because sometimes when you try to do dynamic programming, you will not be able to frame a proper recursive formulation that works for a problem, but you will for the optimal solution to the problem. And that's why we're studying Knapsack. And here, the goal is to preserve some nice recursive relationship for optimal solutions. Optimal meaning solutions that achieve this maximum value. And so the question again is, how do we do this? Oops. So how about, let's take 5 minutes or so. Try to see whether you can apply any of the ideas we used for the previous problem, which is actually very similar to right? In both cases, you're trying to pick a subset that has some nice properties. Think about whether you can apply any of the arguments we've used in the previous problem here. So so Jim Germain, right? This joke where he says, sometimes the way we think about teaching is, pick up 3 balls, I juggle them 5 times, and say, okay, here, I'm done. I brought you on to juggle. And that's kind of what I did. I just showed you, okay, here's how to do some stuff. Now go, you should do it yourself. But let's see, let's see how well we can do it. If you can't, then it's my failure, not yours. Right? So because I should, we should. I want to have you walk through what it might look like, and if you get stuck, then we can walk through how to apply that. So what I'm saying is that subset sum is quite similar to this, but a little bit different. Spend 5 minutes on thinking about, right? Again, sorry, when you start, try to be, at least initially, just try to apply it blindly, even, just to sort of mechanically apply it, and it'll probably not work at some point, and that will tell you something. Don't try to be too clever. Oh, sorry. It'll come in a second. And one way to address some of these questions sometimes is to simplify. So one strategy is to simplify them and even make things, so simplify some of the variables there. So for example, you could say, well, let's assume that can we solve the problem with exactly one of each item, right? And there are other ways to simplify it as well, so we can talk about that as well. Okay. So, tell me what you're thinking about now. So, give me your thoughts. I'm not expecting solutions in 5 minutes. So, give me your thoughts. Yeah?
The first element is that the second element compared to the element which is in that we have greater value than having this element.
So, you're proposing an algorithm. Is this using dynamic programming? Well, in general, of course, out in the world, you can use whatever method you want to solve problems. My goal here is to force you to use dynamic programming. Is that a dynamic programming solution? You describe an iterative procedure, right? Take the first element, put it in. What's the first element?
Which one do you see first?
Sorry?
Which one do you see first?
Anyone. So take any element, put it in. Take the next element, and you said you just kind of compare to the first.
Yeah.
And what does compare to the first mean?
The value.
So you compare the value of the second to the value of the first.
Yeah, I mean the ratio.
Sorry?
Value to be size.
Wait, you just said value. Value or ratio? In percentage.
Ratio.
So take the ratio of the second element compared to the first element. Okay? And then?
So if the second element has higher,
Yeah.
then I will replace it.
Okay, then what do you do?
Move on.
So what you're saying is take the element as the largest ratio and put it in.
Yeah.
Okay, then what do you do? So now what element? Now what? So I just want to point out, there's no recursion. What's the recursion? Or maybe there is. So you have one element. Now what's your recursive step?
So it will be same for all the elements, but we may have like.
No, it's not the same. Tell me what the recursive step is. Be precise.
But at last we will be.
No. I've got one element in the set. You've given me a way to get the first element in the knapsack. What happens next?
Next we will be.
But you can't, because you just said every time you take a new element, put it in, compared to the old one. If the old one is bigger, then you throw out the new one. At this point, you've got the biggest one. Your algorithm is stuck at this point. It will never move the way you described it. Because all you said was essentially take an element and find the one the largest ratio and keep that. That one survives, everyone else goes thrown out. I didn't hear anything beyond that. So your solution is going to be one element. And then I can without too much work, I can tell you what's wrong. Right? Because I can come up with an example where you can put two in. So what I'm trying to get you to do is think, okay, I just give a fragment of a procedure. You haven't given an actual procedure. If you were to write that down in the solution, I would say you've given me a fragment of a procedure. You haven't given me a solution to the problem. You will not be able to prove that this is correct. You will not be able to prove, you will be able to say something was right then, it's irrelevant, it's not correct. Right? Okay, good. So maybe you had something else in mind and you're not saying it. So it sounds like what you want to do is take this element, put it in, and then recursively do something on what's left. That sounds like what you're going for. Is it? Are you sure? Okay, but then if you say recursively go on what's left, what information do you have to know before you can start the recursion? You have to know you've already put one element in. So the capacity of a bag has dropped. So your proposal is find element of largest Vi over Ci and put it in. Are you assuming you have only one copy of every element?
No.
So then you just put it in, or how many times you put it in?
But I think like it's not like at last you'll end up picking the largest element.
No. How many? This first element. I'm not talking about the last. This first element. You said put it in. You put it in once or twice or many times, or how many times? You put it in once and you never look at it again.
Yeah, maybe if it
Okay. So what I'm saying is that if you're going to present an algorithm, and not in class it's fine, but for the homework, right? If you're going to write down an algorithm, these are all things you have to start thinking. Okay. So we're going to try and complete your algorithm. So one idea is find the element largest this. Okay, put it in. Then set C prime equal to C minus Ci, and set the input set. I didn't give a name for the input set. But let's just say S is equal to S minus element I. I've taken this element I out, and now recurs right on what's left. Right? And if you think about it, what this is basically going to do is it's going to greedily sort all the elements in order of Vi over Ci, and then fill them in one by one as long as the capacity constraint is not viable. So that's your procedure. This is a perfectly reasonable procedure now, but it's a complete procedure. If you think about this for a little while, this is what I was mentioning, you will find you're not going to prove it's actually correct because it's a greedy algorithm. and it will actually, there'll be certain inputs which will fail to give the optimal solution because it's greedy. And this is we'll talk about this when we talk about greedy algorithms. But for now, again, let's go back to dynamic programming. If we had to think of this in a dynamic programming, are there other ideas we can come up with to sort of do this? Any other thoughts? So one way to sort of start getting a feel of a problem, I'll come in a second, right, is to say things like, okay, suppose all the elements had the same size. Or the same, sorry, all the elements had the same, yes, same size. Does this make the problem really easy? I see some faint nods, but I'm not hearing why it makes the problem easy. Yes?
You just take the highest value items because they're all the same size.
It doesn't matter. So we know that they're all the same size, like it's easy. Okay, that's good. Suppose they all have the same value with different sizes. Yeah?
I take the lowest.
Take the smallest one.
Yeah.
Take the elements of smallest size and just keep putting them in. That doesn't matter, all the same value. So those are the two edge cases where we can see, okay, things are very easy. Clearly, what makes this hard is that they all have different sizes and values. Okay, so you got a hand up in the back.
Thinking on similar lines to the subset problem, what we could do is we could pick an element and then recurse on the rest of the elements, reducing the capacity of capacity minus this element's capacity. And there could be another path which would not include the element but with the full capacity, and then probably it would return the match of these two paths.
Okay, so I see some nodding here. Did other people come up with sort of similar ideas here? Is that okay? Good. So a number of you were observing this idea that the way to frame this, like we did for subset sum, would be to say, okay, do we pick element 1 or not? Right? In other words, when you say we, I mean, does the optimal solution, so in these kinds of problems, you should know, okay, there is an optimal solution to this problem. It's somewhere. I don't know where it is. But either it picks one or it doesn't pick one. If it picked one, so yes, right? And this is where this gets very interesting. In fact, let me look at the no case first. If it's no, if it doesn't pick it well, then okay, then it's fine. Then you have to look at the set 2 through n, and the capacity stays the same. That's an easy case. Suppose you do pick the first element. Okay. Then the claim here is that, so the optimal solution on 1 through n and C can be broken into pick 1, so you get the value of 1, plus the optimal solution on 2 through n and C minus C1. And this is the thing that is not necessarily obvious, or should not be obvious. In other words, it is not obvious that the right way, that the optimal solution on all items, even if we're told we have to pick one, is constructed by picking one and picking the optimal solution on the remaining items. It could be that one has caused some weird interactions to happen, and so you have to do something else on what's left. Okay? That depends on one. And there are many problems where that actually happens. For example, so if you think of a graph, a clique is a set of vertices that have all edges connected to each other. So if it's a clique of size 3 is a triangle, a clique of size 4 is all possible things, and so on. One problem that we study in graphs is find the largest clique in a graph, right? Find a set of vertices that have the most all edges connected between them. You could imagine doing it, okay, well, either a vertex number 1 is in my clique or not. If it's in my clique, right, then I pick it, but it's not necessarily true that now the optimal clique I have to find the optimal clique on the rest. Well, actually no, I'm not sure about that. Never mind, ignore what I said. But I have to think of another example that happens. But you have to argue that this equality is in fact true. That the optimal solution here, assuming you pick V1, can be written in this form. Okay? And this is where it's different from subset sum. In subset sum, there was just the answer. Here we're talking about the optimal answer. Okay? And this is what is called, this is the key property of a dynamic programming problem or dynamic programming solution. Namely, it's called that there is a substructure that makes that optimal, that to find an optimal solution, you can take off something and then find something that's optimal and what's left and combine them. It is kind of like a dividing problem. It's a recursive strategy, right? It's saying that I can do something here and then bring this up and put them together. But it has to be true in order for you to do this. So we have to argue that this is in fact true. Okay? If we want to complete this argument here for this, the correctness of this recursive strategy. And again, the way to do this is by induction. In this particular case, the key to observe is that if you've been told that you have to pick V1, if we know the optimal solution must contain V1, then we have a bag of capacity C minus C1. And by the way, the way I've written this, if you noticed, I've written in such a way that I'm only picking, I'm picking exactly one item. So this whole N thing is gone. So I'm simplifying a little bit, right? So if I pick it, it's over. So what I'm saying here is that assume that the statement is true for sets of size less than N and for bags of capacity less than C, right? We are told that you must pick V1. We know we can get an optimal solution here. If this was not optimal, the only way for that to happen was that since we had picked V1, we had a better cost solution here magically. But that cannot be true by definition because we have found the best solution. And therefore this works. Because it's just a simple addition. Okay, so again, the statement is, assume that the statement is true. Assume that the property, this equality is true for smaller set sizes and smaller bag capacities. Assume we've been told that V1 is in the optimal solution. The only way this equality can no longer be true is if basically this number is somehow bigger. If this number is bigger than this plus this, it's not going to be smaller. If this number is bigger than this plus this is fixed. Then it has to have found some other solution which is bigger, which contradicts the fact that this was the biggest solution you could find for everything else. And therefore you have. Yes?
How do you know that when you pick one, V1, and you just left 2 to N? Because I can pick 2 of V1.
That's what I said. That's why I said in this formulation, I'm assuming that we are only allowed to pick one of each thing. I just said that very quickly, I think. So my point was that I'm looking at a simpler version of the problem where I'm picking exactly what we think. But you are absolutely right that in fact you could change this and pick this thing. And so in fact, maybe this is a good point to ask. What would you do in that case? It doesn't take actually much to modify this recursion, but what would you do?
I still need the optimal second left.
Yeah.
Just include V1. I still include 2 from 1 to N.
Right.
And the value capacity is C minus C1.
Another way to say this, well, it'll be C minus that many times C1.
Yeah.
Right. If I add V1 more times, it piles up more capacity, right? Yeah. Another way to say this is that we were guessing whether we picked 1 or 0 copies of 1. If we're allowed to pick more, we have to guess the actual number of copies we have to pick of 1. And so it could be 1 or 2 or 3 or 4, and you have multiple choices for each of them. So in particular, you could have a different version. That's why I like to sort of explain the simple case first and then the real case, because once you buy this, you can say, well, the real case is going to be how many. Sorry. So can we give an upper bound on how many copies of 1 we could possibly end up picking in any solution? Yes? How many would that be?
I would have C divided by C1.
C divided by C1, right? So the number of choices of picking the first element is basically, 0, 1, 2, up to C divided by C1, right? Yes? For each number of ways to pick, let's say we decide to pick k copies of V1, right? Then the recursive step would be, then we'd be looking at a recursion which would have C minus k times C1 and the set 2 through n. Yes? You agree? And you do that many copies of the recursion. Okay? So handling the case, so one of the reasons why it's helpful to try and simplify is to say, okay, where is the irreducible complexity of the problem? Right? We're not fully done with this yet, but as you will see, clearly setting all the sizes to be the same makes it too easy. Clearly setting all the values to be the same makes it too easy. But setting the choice of picking 1 versus 0 or 1 versus many copies doesn't seem to make it that much easier. But it does make it easier for us to think about it. So as a design principle in algorithms, it's often helpful to find, okay, what's the simplest version of the problem that's still hard? Solve that, and often you can layer on the rest of the stuff afterwards. And that's what we can do here, like in this case. Like it's okay, I can handle the multiple choice case just by this. I'm not done yet. Okay, so let's continue. So now that I've done this, I have all these recursive steps, right? Either I have those 2 recursive steps, or I have many, I have, kind of C over C1 plus 1 recursive steps. That's the recursive formulation now. Now what do I have to do in a dynamic program? What is my next step? I'm not done, right? Because that's many, many recursions. That's going to be a lot. What is the trick? What is the thing to try and investigate now? Sorry? Good. So what does a subproblem look like? In other words, when I do the recursive call, what are the parameters to the recursive call? The parameters to the recursive call are a set and a value. Now if I say it that way, that's terrible, because there are many, many possible sets. But it's not a set, it's a suffix, just like the subset sum. I can describe that set by a single number, the first number that it starts at. So in this case, it's 2 through n, so I can give it the name 2. Right? It implies everything from 2 to n. The other number is a number from, 0 to c. And we'll assume everything is integer. How many total subproblems do I have? N times c, right? So the total number of subproblems is n times c, which is great. This is very good. This is exactly what we wanted. We wanted a small number of subproblems. Okay? Okay. What's next? So we've done the recursive formulation. We've verified that it works correctly. We've done the observation that there actually are not that many subproblems, but they overlap. What's the next thing we do? Pardon me?
So are we doing running time now?
Not yet. We don't have an algorithm yet. Okay. So, but the next thing we do is try to formulate what the actual algorithm is going to be, as opposed to this recursive way of thinking. So, what do we do to do that?
Solve the easiest of the subproblems and build other subproblems on top of them.
So, very good. So now, if we look at the way our recursion is going, where are the easiest subproblems going to be? Yeah. Go ahead. You're about to say something.
The last.
So what value of the first parameter will that correspond to? Which we are right at the end. It corresponds to n, exactly. And what about on this side? 0, right? So the end cases of this. So now let's make our table, right? So we have these 2 parameters. So now we can say, okay, I'm going to make a table. On this side is going to increase in C. On this side is going from 0, 1 up to n, right? And so we know we have an index into this table for every value of N and C. So we just have to make this table here. Oops. And what we just said is that the cases where we know what to do are the case when C is 0. And the case where we have just one item. Right? If C is 0, so what is the value we're going to put in there? What is the number we're going to put in there? It's not a now, in the case of subset sum, it was like a binary thing, right? True or false. What are we going to actually put in here? We're going to put in the value we get, right? Okay, so the capacity is 0, what's the value we're going to get? It's going to be 0, right? So we're just going to put a whole bunch of zeros in here. It's going to be a 0, 0, 0, 0, all the way to here. Now, if you look at this side here, right? You're just picking the last item, and the capacity changes. What are you going to put in there?
Value of that particular item.
And it's much more complicated than that, right? Right. So start from capacity 0. Capacity 0 is 0. It's going to stay 0 till
the element that is value.
no. There's only one element, right? Remember, at this stage, all I'm saying is, look, I have one element, element n, and I'm checking to see whether I can put in the bag. So it's going to stay 0 till of that element, right? Very good, very good. So it's going to stay 0 till we get to the capacity of that element. And then you'll put the value of that element in that cell, because now I can put one of it, right? So now I can put Vn here. Now, if we're only worried about 1 versus 0, it will stay Vn all the way to the top. If we're allowed to put more, what's going to happen?
Two of Vn.
Where? First, it'll be Vn, and then 2, and then, right? Because the capacity has to increase to handle 2 times that capacity. So it'll be Vn all over here, then at some point it'll be 2 times Vn, at some point it'll be 3 times Vn, and go on like that. Now we have filled in the base cases of the recurrence, right? The easy cases, as you all pointed out. So you've got the here and here. And now, okay, let's just, we're going to fill it out, right? So let's just take an imaginary item somewhere in the middle, right? So there's some item in the middle here, and we want to fill this up. What elements is it going to be looking at to fill itself up? So we can look back at the recursion, right? So let's look at the simple recursion first, the case when you just have 2 cases there. So we know that it's indexed by some value I, right? So in one case, the index I stays the same, but it looks down. In one case, the index I moves up, but the capacity requirement stays the same. In one case, the capacity requirement goes down, and it goes to the next one. So in other words, if you have to look, every element is going to look at either an element one step across, which corresponds to not picking it for the set, or an element a little bit further down, which corresponds to picking it for the set, just like in the case of subset sum. The difference here, though, is that how do I update this value? So I have those 2 values, right? So I have this value here, I have this value here. How do I update the green one from the 2 orange ones?
Max of the 2 plus this value.
Well, max, you're like almost right. It's not max of the 2 plus this value. It's max of that value and this value plus that, right? So the max is outside those 2 things, right? So in other words, this value will become the max of either this, because you didn't pick it, or this plus the value of the item, right? So again, if we look at our formulation, which we didn't actually explicitly write down, which we'll write down right now, opt of I and C, right? Now I'm writing in the language of the indexing of the table, is equal to max of opt I plus 1 comma C and opt I plus 1, comma, C minus Ci plus Vi. Okay? And this is the precise formulation of how we're going to update the table. Does this make sense? Because if we don't pick item I, then everything stays the same, we just pick it. If you do pick item I, then you update. We don't know which one, but the dynamic program will tell us which one to choose. Which, by the way, also tells us how to do the backtracking. Right? Because now we know, if we pick this one, we did pick I. If we pick this one, we did pick I. We can attach the pointer appropriately when we have to backtrack. And now we're done. And this is again in the case of picking exactly one copy for each item.
So as you fill the bag, it should kind of step down.
Yes, exactly. You don't know which way it's going to happen, so you're filling it up. At the end, it's okay, where are my arrows coming from? Now, yeah, drag them back down. Yes?
I'm sorry, I don't understand the V of I plus V of Y.
Okay,
The second term.
right. What we're saying is that either we decided to pick the ith element as part of the solution or not. If we pick the ith item as part of the solution, then we get its value, right? Which means that we get its value plus whatever other value was from the remaining items. If we did not pick the ith item, we don't get its value. Make sense? Yeah, good. Okay. All right. Stop here. I want you to ponder how you adapt this to the case of the multiple choices. One thing to remember is I'm making the choice up front, so I could essentially run this table calculation for each of those choices. And how that works in the case of dynamic program, I'll leave you to think about it. We'll talk about this more. Okay? Yeah. All right. I will see you then. And we have, I also